While you're finishing your lunch, we're going to have a speaker. And to introduce the speaker, we have Carla Hesse, who is Dean of the Division of Social Sciences in the College of Letters and Science. Carla?
Well, thank you, Carrie, and thank you to the Travers family for making this wonderful event possible, and so many other things at Cal, both mind and body. And it's a great pleasure to be here and to see all these people out here for such an important topic. I'm delighted to be able to join for a little bit of time and to get to touch bases with one of my favorite departments, political science, which is doing fantastic things and in a process of just self-reinvention that's exciting to watch. As I was just saying over lunch, that Cal is in a moment of generational reinvention. It's not just that we're being reinvented in the face of the changes in our financial situation, but it's also a moment, in which there's really a handing off of the baton from the baby boomer generation to the, I guess, X and Y and millennial generations. And I feel like I'm sort of in this liminal generation between boom and X, and it's my job as dean to be an intercessor. And watching that happen is just astonishing and electrifying. And so it's been wonderful to watch that happen in this department. We've got lots of hot recruitments going on this year, and that's the kind of problem a dean likes to have. And even retentions, which is the kind of problem a dean likes to have. I always tell you, if people aren't coming at us, I'm worried. So it's a great pleasure to be here and to see people focusing on a topic of such importance. And I'm really delighted that the Commonwealth Club could in some way partner with us in this event, and I hope that will continue to be the case. Finally, I have the very special pleasure of introducing our keynote for the conference today, Dr. Jane S. Long. Dr. Long recently retired from the Lawrence Livermore National Laboratory, where she was the Principal Associate Director at Large for the lab's Center for Global Strategic Research, and she was also the Associate Director for Energy and Environment. If I think I have a big job, that's a big job. She holds a bachelor's degree in engineering from Brown University, where she was recently honored as the School of Engineering's Alumna of the Year. And she holds master's and PhD degrees from Berkeley. She's currently a visiting researcher at UC Berkeley, and that's only one of her many engagements. She is also involved with the Environmental Defense Fund and with the Bipartisan Policy Center. And she co-chaired the California Council of Science and Technology's California Energy's Future Committee. And I think today her topic is going to be sharing with us some of the highlights and conclusions that emerged from the committee's work. So I'm really looking forward to hearing her remarks. And I present to you Dr. Jane S. Long.
It's a great honor to be here today, and it's incredibly relaxing. I gave this talk yesterday in Sacramento in a convention hall, which was separated from three other talks by curtains, and the video didn't work and the audio didn't work, and it just feels so nice to see my slides up there, and the fact that you can hear me, it's incredibly better. So thanks for having me today. I'm going to talk to you a little bit about the study, which was about reducing, about the long-term, goals of energy. And I'd just like to start with how many people understand what the bathtub effect is in climate change? This is perhaps one of the single most important parts of the climate change problem. And every time I give this talk and ask people in the audience if they know what it is, they don't. What it is that when we put carbon dioxide in the atmosphere, it more or less stays there. So it's not like any other pollution problem that we have. Most pollution problems, if we taper down or we stop, the problem goes away. This problem, the more we put up there, the more we have a permanent, relatively permanent problem. where permanent is on the order of 1,000 years. So you can't just slow down. The problem will continue to get worse until you stop altogether. And that fact is really lost on, I find is lost on a lot of people. And just to show you a little bit of data, these are two curves published by Susan Solomon, who headed up the IPCC conclusion that said that the year that it came out with man is causing climate change. And here you see various curves where she posits we stop emitting CO2 altogether at a moment in time. And then the bottom curves a whole set of things of what happens with temperature. And basically, the problem sticks around for many, many centuries. So the only way to stop making the problem get worse is to stop emitting altogether. So that's one parameter of the study. Another is, on what scale should we try to look at this study? How many people think that the that the UN process for controlling climate change is working? Good, you all get A's. How many of you have taken an action yourself to save energy? What do you think the impact of what you do is very, very small individually, even though you're completely able to walk. The cameraman raised his hand, just note that, please. The impact is small, but you're able to make a choice yourself. You're able to have agency and make a choice that will save energy. On the world level, if we could do that, it would make a huge impact, but we don't have the agency, can't do it. So what happens is that someplace in the middle is this incredible sweet spot of the regional control, regional analysis, regional ability to do something which still has an impact, but it's a struggle to act, but we still can. So the point I want to make here is that it's really important to think about regional solutions. And in California, we have this going on. You all know AB 32, but many people don't know that we also have a governor's executive order from Arnold Schwarzenegger, which asks that we reduce emissions by 80% below 1990 levels by 2050. And this is an enormous cliff that we're going through, because it means basically 90% per capita reduction in emissions by 2050, when you count for a little economic growth and a population growth. So I like to describe it, I'll have to get an overhead that does this. We're talking about this ramp that we're on, and people trying to make decisions that get us on a ramp. But when you start looking at 2050, it's a cliff. And we have to figure out how to do it. Well, what does it mean? The important thing is we have this goal. We have a goal that says reduce emissions pretty much entirely. I mean, you aim for 0 and you miss by some, and maybe you make 80% below 1990. But if you're not going to emit, it means you're not going to burn fossil fuel. I mean, that's just the way it is. And the only way you can burn it is if you somehow sequester the emissions. And so you got to find a way, you got to find an energy system that works for you without coal, without gas, and without oil. Or if you use them, you have to sequester the emissions. So how do we make decisions generally about energy? We generally make them in a triumvirate of interest groups. We are concerned about how much it costs. We're concerned about energy security. We're concerned about the environment. We're concerned about climate. And in this case, our goal has been, again, by Governor Schwarzenegger, to reduce emissions by 2050. And so what we say is that we should go to 0. The climate problem demands that we go to 0 as fast as we possibly can. And the way in which we make decisions about energy demands that fast as possible is going to be around 2050, we hope. That 0 is really about 80% below 1990, and we want to try to do this while keeping reliability. When you turn the switch, the lights go on, about what it is today. And then the last piece, because we really can't predict what things are going to cost in 2050, try to just at least rule out the choices that would be wildly expensive. So what does that imply? Well, I think our committee met for 2 years to come up with this little list. This is a 4-step process to count. How do you count? People like to count in a lot of different ways, but we wanted to count in a way that counted everything in the energy system and only counted it once. And that's actually pretty hard. I'll give you a couple of examples. Transportation people who like to work on transportation energy, they like to work on the vehicle miles traveled, the efficiency of the vehicle, and a fuel that's a low carbon fuel. Well, you know, the vehicle's mile traveled is not a technology issue, it's a behavior issue. This was, for us, a technology study. It's a valid point, but we didn't want to convolve behavior change with technology. We wanted to first see if we had the technology. And the fuel, the biofuel, well, you know, then the people who do electricity, they want to use it to have a low carbon fuel to balance load. Or somebody else wants to use it for recycling. And so the demands on biofuel will be multiple and varied. And we wanted to make sure that we could count them only once. So despite the fact that people in transportation energy were very unhappy with us, we wouldn't let them analyze or count biofuel. We counted everybody's needs for biofuel all at once. So that's what this accounting measure, this accounting is. It's 4 steps to stop burning fossil fuel unless you sequester the emissions. And the first one is, obviously, you try to do the same amount of work with the least amount of energy. That's an efficiency measure. And then secondly, you try to shift all the energy needs over to electricity because it's easier to get decarbonized electricity than decarbonized mobile sources. And then that doesn't do any good at all. You know, a zero-emission electric car is not a zero-emission electric car if the electricity it's using is coming from a coal-fired plant. So you have to decarbonize electricity. And then you have to also take account of the fact that it's not just a capacity problem, there's a system integration problem and a reliability problem, and we have to deal with load balancing. And our study tried to look at load balancing a little bit explicitly as a possible source of emissions, so you've got to remove emissions from the load balancing part. And then finally, you probably still need fuel. And so we looked at the ways in which you could decarbonize our fuel supply. So let me walk you through a few of those. But just to preview, the short answer is, can you do it? Yes, you can do it, but it's really, really hard. You're going to see that to get about 60% of the way, we can use technology we more or less know about today, but that to get the rest of the way is going to require a lot of innovation. Can we envision how we could do it? Yes, but it's going to be very hard from a matter of will to apply the things we know about and a matter of innovation to develop the things we don't. So let me show you a little cartoon that shows this. Here you see our carbon footprint from energy, where the rectangle on the left would be fuels, and on the right is electricity, and the y-axis is carbon footprint of the electricity system. And then what we're going to do is squeeze it to make it efficient. We'll use less of each of fuel and electricity. And then we're going to shift it towards electricity. And then we're going to decarbonize the sources of energy that we have until we have a much smaller footprint. And this is actually scaled just about right. We're going to go to about 10% of our carbon footprint. So with that, we then looked at the technologies that were available to do these 4 steps. And we bin them into these 4 bins. It was either you could go out and buy it now at scale, or it was at least been demonstrated. And occasionally we had to dip into the 3rd bin, which is it's just in development. We did not dip into bin 4, which is a research concept. There's some wonderful things out there that could solve all our problems, but they won't be here by 2050. And again, getting to 0 by 2050 is pretty strong, or close to 0 is a pretty strong imperative from the climate perspective. So then we did a bottom-up study. We started looking at all these sectors and asking, where could we be more efficient? Where is it technically possible to get more efficient? Where is it technically possible to electrify? And I'll just give you a couple of examples of the data that comes out of this without going through extensively. There's data on the web at ccst.us. And if you look for the California's Energy Future Studies, you'll see a whole report on the efficiency and electrification in that group of reports that give you a lot more detail. But here you see that this report says it's technically possible to change every square foot of building in California. Every square foot. You can either retrofit it, or you can tear it down and build it over again, or you can build it from scratch. And if you do that, you will get energy savings. And I think the most remarkable thing about this graph is that about 2/3 of the energy savings are projected by, this is work done by LBL, to come from new construction, either stuff that's been torn down and rebuilt or new construction. And about 1/3 of the energy savings comes from retrofit. But I'm pretty sure that the vast majority of the cost of this comes from retrofit. And I think that's an interesting piece of data. I think that's worthy of more stronger look. On electrification, I think most people are pretty clear that transportation is going to be electrified, and this is just a plot from Davis, work by Chris Yang, looking at how the fleet might become over time increasingly electrified to the point where our average fuel economy would be 75 miles per gallon. And so here it is. Here's a kind of summary of where it's all coming from. The point I want to make is that it's not just automobiles. You're going to have to electrify a lot of things in your house. How many of you heat your houses with natural gas? And how many of you cook with natural gas? So you're going to be all using electric if this goes through. You're going to be doing the entire transportation system either electrified and made more efficient, with a couple of interesting exceptions. We don't have electric airplanes, although I did note that somebody's testing a solar airplane soon. I'm not sure I want to go cross-country on one, but ships, hard to electrify. So there are going to be some remaining uses of fuel, likely. So the first big question I want to pose that comes out of this study is, where is the biggest bang for the buck in all of this? This is a massive change in what we're doing, and I don't think we think about where we can get the biggest hit. The most obvious example for me is a high-speed rail system between two cities in the Central Valley, and no money for electrified dedicated bus routes between San Francisco, Marin, and somebody's going to clap. I mean, this is a massive change, but you certainly don't want to put your bucks behind stuff that isn't going to make any difference, and certainly not a lot of bucks. So that's my first question that I think society needs to start to turn to as a matter of ethics and accountability. Where is the money going? So after we've done all this electrification and efficiency, it changes the demand structure. So the next thing we're going to do is look at where the energy comes from, but now we've adjusted the demand because we've made everything efficient and electrified it. So if you look on the left, you see the 2050 BAU, business as usual demand, and cut it significantly by efficiency measures. Radical efficiency measures are not really even cutting it in half, but pretty significant bite at the apple. Meanwhile, then we turn around and electrify everything and reverse it all and even make it worse. So basically, you're going to double electricity and decarbonize it. That's the challenge. And on the right, the fuel, when we made things more efficient and then we electrified, we did a lot to get rid of our fuel demand, but that orange line is the fuel demand, is the demand level today. So it's something like 2/3 the amount of fuel today in 2050, just because of population growth and economic growth. So you can't get away from fuel, even after you've changed every building, you've done all of this stuff with energy efficiency and electrified all the cars. You still couldn't electrify the heavy-duty transport, ships and airplanes, and you're ending up with a pretty big hit on fuel. So now what are you going to do? Well, first thing you're going to do is work on electricity, and here's the challenge. It's just a little challenge. Take the whole electricity system we have today and double it and decarbonize it. No problem. So we looked at 3 different portfolios of electricity, and you can decarbonize electricity basically in 3 ways. You can use nuclear power, You can make fossil fuel generating plants, thermal plants, capture the carbon and sequester it underground, in other words, CCS it's called, where you take the carbon out of the flue gas and pump it underground where it hopefully stays for a long time. And then the third way, which is the way that the state is pretty much committed to, is the renewable energy challenge. So these are very different choices. And we have to think about these carefully, I think. So one thing is that we need roughly 50 gigawatts of new capacity in the state by 2050, according to this model. And as well, about another 33%, that would be only 2/3 of the energy, another 33% would come from renewable energy. Since that's the law, we never looked at a portfolio that didn't have at least 33% renewable. So if we have to build 50 gigawatts of new power beyond that 30%, we either build around 44 gigawatts of nuclear power, because nuclear power runs all the time, so you don't need as much. It runs mostly, 95%, capacity factors of around 95%. And I'll explain what a capacity factor is. So if you have a nameplate on a generating plant, so it's supposed to produce a gigawatt, it can produce a gigawatt of power, and it only runs 95% of the time, then its capacity factor is 95%. Well, in the case of fossil, it's not quite as good, but it's pretty good. When you get to the renewables, the capacity factors drop dramatically because the wind doesn't blow all the time and the sun doesn't blow. The sun doesn't shine, the sun doesn't blow. So you have to build about 3 times as much to get the same amount of energy. And then there's the second problem, which is that you still have to have a way to make sure that demand equals supply at all times. So electricity is unique among the resource problems that we face in that the supply of electricity has to match the demand at every instant. And so that problem of trying to make that happen when you can't control when you're going to get the power is the issue. So just to speak a little bit about the issues on the others, and I'm going to come back to the renewable problem. The nuclear power problem, we had a committee who looked at all the technical aspects of building out nuclear power, 50 gigawatts of nuclear power, and saw no technical obstacles in doing that. That's not to say there aren't obstacles. Well, one is that it's against the law in California to build new nuclear power until there's a solution to the nuclear waste problem. And I've been involved in that my entire career, so I think that's largely a political problem. And the other is that there are a lot of institutional issues. While we were writing this, right after we had published the report, the Fukushima accident happened. And I was very, very honored to meet the Japanese medical doctor, who headed the commission for the Japanese diet to examine the root causes of the Fukushima accident. And it's absolutely remarkable what came out of that report. He basically said this was a man-made accident. It didn't have to happen. It had to do with the way the institutions were constructed, the way there was a collusion between the operator and the regulator, and the way that choices were made. And nothing that happened there had to have happened. It was all a matter of institutional and cultural issues. And I think that characterizes the nuclear power problem. Technically, people know how to do pretty much anything that we need to do it, but it is an institutional issue. On the fossil side, there are 2 issues. One is that we know how to do all of the pieces of things that we would have to do to make electricity with a fossil fuel, capture the flue gas, capture the CO2, and put it underground. But we have not put together a plant that's integrated at a large scale and actually done it. We need demonstrations here very, very badly to make sure we get the kinks out of knowing how to do it. We know all the pieces, we don't know how to integrate it. Second problem is you don't get all the flue gas. So you'd be lucky to get 80 or 90%. It's very costly. The major cost of this whole CCS thing is the capture. And to capture the next 9% out of the 10% remaining would cost as much as the first 90%. So you have to put up with some amount of emissions, and that's an issue. So let's talk a little bit more about the renewable one, the problem there. One of the things that's really true about renewables in California is we have plenty of them. This is the portfolio we used for projection into 2050. And you can see the resource upper limit of 100%, that we're barely tapping into what we have. We are the Saudi Arabia of renewable energy here in California. We have all kinds, and we have plenty of it. So that's not the issue. It's not a capacity issue. But this is an issue. And this is what I mentioned a few minutes ago. Here you see the capacity factors. And for the portfolios that we see, that we looked at, which are a projection of the kind of portfolios we have today, percentage-wise, our average capacity factor is 30%. We're lucky, because the average capacity factor, for example, for wind power in Pennsylvania is around 10 or 15%. So we have very high capacity factors, but we still have to deal with a big piece of it. Then the two on the right are very interesting. The biomass issue, as you're going to see, one of our themes is everybody wants the biomass, and there's not enough. So that's a great way to have dispatchable power. You can burn it whenever you want, and burn it when the wind isn't blowing, but everybody wants a piece of the action. And the geothermal, I think, is fascinating because we could really exploit. We have the largest geothermal plant in the world here in California at the geysers. We could certainly push this much harder. Of all the renewables, this is the one that would solve a huge problem with renewables, and we should be pushing this much harder than we push it. So what do you do about it? Well, there's three ways to deal with this intermittency problem or load balancing problem, and we incidentally call this the zero emission load balancing problem, ZELB, and we think it ought to be really thought of as a sector of the energy industry that ends up being treated as something that has emissions you have to deal with. So basically you have three ways. You can get a turbine and burn natural gas when the wind isn't blowing and the sun isn't shining, and that's going to create emissions. Or you could try to do it with CCS, but then you have to build the entire infrastructure for CCS and only use it when the wind's not blowing, so it'd be really expensive. You could use some biofuel here if you got the biofuel signature down, carbon signature down very low, but then again, here's the theme again, everybody wants the same biomass. And then the other way to do it is to have energy storage, which you've heard a lot about, I think, this morning, and that's a cost problem. It's expensive. I don't remember the statistic, maybe somebody in the audience knows it, but I think Bill Gates has the statistics that if you take all the batteries in the United States and fully charge them, that's 10 minutes worth of electricity in the country. So this is a massive problem to do storage at a utility scale and very expensive. So we'll have to think about how we're going to solve that. And then the flexible load problem, which is all the things you were hearing a little bit on the last panel, where we try to noodle when the electricity is actually demanded to be when the electricity is actually being produced, and have people shut down when you don't have enough electricity, and manage that whole system and be able to grab the wind power from a place over here when it's not blowing over there, and the transmission required for that. These are incredibly going to be a very, very difficult transition, probably a bigger transition than, how many people here remember when Ma Bell owned your telephone? Yay, some old people here. So, I mean, basically the whole transition from Ma Bell to everybody having their own little device that's in their pocket is nothing compared to the transition that we're going to have to go through to make that actually work. So we have these three methods, and we're not really sure how they're going to work yet. So we just said, oh, well, how big's the problem? And we said, let's say for these portfolios, and on the left you see a median one where we use about a third nuclear, a third CCS, and a third renewable. How big is the issue? And so on the left you see what happens if you are able to the legend is reversed. The light blue is what happens if, how many emissions do you get if you firm all the power with natural gas? So every time the wind isn't blowing or you want to ramp or do anything else, you do it all with natural gas. And the bar on the right in each case is if you do it somehow with zero emission load balancing. We didn't say how, it doesn't really matter for this, just how much. And so what I want to point out to you is that for renewables, the size of that gap is pretty close to the size of the target for the whole energy system. So as you ramp these emissions down, what becomes important changes. And here, when you ramp this down to getting close to 80 or 90% cuts in emissions, the emissions that come from load balancing become a very large part of the problem. So what we learned here is it's a problem you have to solve. So what I'd like to point out is I think we have electricity choices, and those choices are pretty significant. We don't have nuclear power on the table in the state right now, and that has some impact. Coal with CCS is not happening yet. There are companies that want to come in and try to make this happen. There are companies who want to do what's called CCUS. U stands for utilization, so carbon capture, utilization, and storage. And the utilization in this case is pumping CO2 into an oil reservoir in order to produce oil. But the CO2 more or less can stay there. And so we do sequester CO2 that way. And we could, in fact, CARB has declared that oil produced that way would be considered a low carbon fuel because it sequestered the CO2. And so that has to get started or we won't have that technology available. And that's an issue. And it's, it may get started, but it's pretty dicey. These are dedicated people who aren't just, who companies are coming in that's not just to make money. There are people who really believe that we need this technology, and they're willing to not make a lot of profit, but they can't make a business deal that makes no profit. And so we have to have a way of getting forward. And then on the renewable side, the question is when you buy the capacity goals, the RPS, or the governor wants so much distributed energy, do you also buy the other part of the problem, which is making sure that it all works? And so the equal effort on that part needs to take place, which leads me, well, I talked about that, so I won't do it. Leads me to the second big question, is how do you choose? I mean, what is the right way to go about thinking about the impacts of these technologies and which ones would actually do better? And there's other issues. It's not just how hard they are, but how long they would take. It could be, for example, that a long-term, century-long goal of having 100% renewable energy is a fantastic goal, but it might not get you to 2050, it might not be done by 2050, and that's a problem. And so maybe you want to think about what the impact of taking things off the table is. Finally, I'd just like to say, I think that defining differences are not going to be capacity. I want to emphasize this again. We can get the capacity any way, any of these three methods. The issues are going to be integration and institutional and reliability and how much transmission we have to build. These are the things we need to focus on. So that's the second big question. Finally, we were left with that fuel problem. Remember, we electrified everything out the kazoo and made everything really efficient. And in the end, we still needed 27 billion gallons of gasoline equivalent in 2050. And so we looked at all the biomass, and I'll just show you a little analysis of that. Here's all the kinds of biomass you might use that wouldn't have necessarily an impact on agriculture. So there's all waste materials and crops grown on marginal lands without irrigation, without fertilizer. And so you can use them in all different ways. This is just a flow chart of showing all the different ways you could funnel those biomass products. And what's not in there is, for example, the MSW, municipal solid waste. If we actually try to do that, there's a significant contingent in the state who will say, no, you can't have that waste. That's my resource. I use it for recycling. So there'll be a huge amount of tension that has a history in environmentalists not wanting waste to be incinerated, that will come back to haunt us, and has come back to haunt us in this. So there's actually been companies come in and say we want to be counted under the renewable energy standards to gasify municipal waste, and there were And so we want to qualify, and then politically they're countered by people who say, no, that's not right. This should be recycled. So there's a need to look at that. So we figured we could get about 3 to 10 billion gallons of gasoline equivalent per year out of that stock of biomass. And I want to point out that that is a upgrade from what CEC thinks. It's much more than what CEC thought we could get. But it turns out that about 2 billion gallons of that, or 3 gigawatts, really is not suitable. It's not economic to make it into fuel. So that'll go directly to electricity. And then, well, you know, we had some rules about importing. We said in our study, you know, you can't import more than your fair share. You have to assume that everybody else is doing what you're doing. Well, we're 10% of the country, so maybe we could import some, and maybe Brazil will ship some out. People in Brazil in the biofuel industry that I know tell me that they're not going to be exporting. They're going to use it themselves. But let's just, you know, for the sake of argument, see what it is. And that's, you know, roughly 13 billion gallons, or about half of what we needed, and we were pretty optimistic. So I think the chances of us having enough biomass to meet all of our biofuel demands in energy are pretty low. And that's a significant problem. So the third big question, how do you fill the fuel gap? And there are 2 parts to that. You know, the biofuel has all this potential, but we're not really on a path to actually even get that biofuel very well. The biofuel companies are not gearing up that way. And secondly, what happens to the rest of it? And that's the largest innovation problem that we face. Where is the fuel going to come from? So basically, just to review where we got to on this, this is the way we're going to go if we don't do anything. We'll be up around 840 megatons of CO2 per year if we don't take action. If we only did one of these things, you constantly hear things like, well, we'll just do it with efficiency and change and electrification, that's all we need. Well, we actually asked people to look at that, and there was no single action. Even when we sent these things to absolute stress test, there was no single strategy that would get us anywhere near the target. And so here you see the hit you can get with any one of them, and none of them come anywhere near the target. But when you sequentially add the efficiency, electrification, low carbon electricity, and low carbon fuel that we think could be available technically by 2050, you get close to the target, but you still don't make it. Well, how are you going to get the rest? The rest is going to be hard because it's going to involve technologies that are either complicated, expensive, or not really available. So some of them will be transformative. I think in energy there is a silver bullet out there. People always say there's no silver bullet, but I think there is one. I think if we ever got fuel from sunlight going, that's a silver bullet. But some people think that's 100 years off. Some people think it's 500 years off. It's not going to help us to get to this target in 2050. Fusion is not going to help us to get to this target in 2050. It's going to be these other things, and they tend to be complicated. For example, you can get a pretty nice hit from taking, on paper, from burning coal and biomass and using that process to produce electricity and fuel and then sequestering the carbon dioxide. It's very efficient on paper, but boy, is that a complicated industrial condition. So can you really do it? There's people looking, there's some things not on this list. One of the people that I've been working with is really interested in ammonia fuels, although after last night, I'm not sure they should be as interested in ammonia fuels. But there are all kinds of ideas out there. So one of the things that we think is important to do in that third big question that I put up there is that how do you fill the fuel gap, is we need to think through, gather ideas about filling this fuel gap and try to figure out which ones are the best bets. And I think that's a project we'd like to do. And just to show you that you could get there, by adding multiple of these very complicated things together, you could not only get to the target, but you could get below zero. And that would be a really nice thing. But this is probably as much effort, so the last 20% will be as much effort as the first 60%, as a rule of nature. So just to take away the 60%, it's really hard. But we know how to do it. It's a will problem. The 80% is an innovation problem. And I just want to reiterate some of the issues about regional planning, because I think you have to remember what it is that will make this work. One is having a goal. The whole fact that we could do our study was because the governor signed this executive order. We had planned to follow the National Academy of Sciences' America's Energy Future Study. That study is a great study, but it's this huge tome of things without anywhere near the kinds of conclusions we could draw, because we had a goal and we could compare what we could do against that goal, and it could reveal what the issues were. So having a goal, knowing where you want to go, as they say, if you don't know where you're going, you might not get there. I think it's really important strategically to have goals. The accounting really matters. That was the hardest thing we did. I think it's the thing I am singularly most proud of in the whole process, is that for a group of 40 experts to come together and agree on how to do the accounting took 2 years, and it was really, really important. Count once and count everything. You've got to think about the boundaries, especially as we add up these regional plans. They will not come out to a net gain if you, like San Francisco, claim to reduce your emissions by 20%, and the way you do it is decide not to sell a Hetch Hetchy reservoir power to anybody else and just use it for yourself because it's emission-free. Then everybody else just puts gas-fired plants on and you gain nothing. So don't leak. And don't take more than your share. Everybody has to do this. And the final thing is, it's really important to think about what the right questions are. We don't know the answers to those 3 questions that I gave you, but I'm pretty sure that those are 3 important questions. And that focus is really important. Thanks.